Nice greetings to everyone, and welcome to my lecture on the topic, which is, I would say, now rather well known, but still interesting. The work that we are doing is done in the framework of a wider project and falls in this subtopic where we try to improve existing and develop new models for estimation of various advanced material parameters and properties based on those that are more easily available. Speaking concretely, we are dealing in this research with aluminum and titanium alloys. We have done extensive work on steels, various subgroups of steels. Now we decided to extend something that we have done also to these alloys, as they have quite a big importance, especially today, and is expected in the future in quite important industries. Lightweight and fatigue-resistant designs are essential in these areas, and with this comes also the need for reliable, accurate as possible material data. Unfortunately, or whatever, these data are difficult to come by. Tests are expensive, long-term, long duration, and everything that goes with it. So that in some cases, especially in early stages of product design or later in some sort of analysis of existing structures, people try to use the estimation methods where, as is usually the case, we try to do something complex, but in more easy and cheaper way, and try to save us expense and trouble. This is again, focus is on strain life approach regarding the fatigue and extremely well-known Baskin-Coffin-Manson equation, which is given here. And the idea is that there might be a possibility to estimate fatigue parameters and fatigue behavior, consequently using easily available and static properties, monotonic properties with, I would say, reasonable accuracy. So this also has to be, in the end, tested with experiments. So we cannot rely exclusively on such simple methods, but they can be useful. The idea is, of course, not new, as can be seen from this list here. So there is approximately 50+ years of development of such methods. The first two were proposed practically at the same moment. So original universal slopes method, their 4-point correlation method. I won't go through all of them, but quite a nice number has been developed over years, with the most recent additions, as far as I know, in 2018. Again, the same methods, of course, are developed for different material groups and subgroups. The list is shown here. We can see that, of course, not every method is intended for all materials or every material subgroup. This is, of course, well-known information is provided by the authors, and for most of them, there is also a certain validity range, so applicability range within which, regarding the monotonic properties, these estimation methods are recommended to be used. For some of them, this is not explicitly specified. So again, there is certain amount of unknown information, but using reasonable thinking helps in any case. Again, additional factor that we have to consider is practicality. Again, we like to do things easy, simple way. So if we have to decide which method to use, the chances that we will use the most practical one, the simpler one. And in this case, these are the methods that use the least possible number of monotonic properties, which some of them, like true fracture strain, true fracture stress, are again not easy to come by. Very often in literature, these data is unknown, and also if we have to do some testing, this requires additional effort. Of course, the topic of today's talk are primarily methods which are intended for aluminum and titanium alloys. These are here, but we would also like, for this, we wanted to keep things also practical for this initial phase of the research. So we focused only on these 4 individual estimation methods for which we need only Young's modulus and ultimate tensile strength, because there is some additional aspect of this method and their application, which we would like to emphasize as a basis for the future research, which is coming next. So once that we have narrowed down the methods that we would like to use, the next question is the accuracy of these particular methods. And this we have to sort of judge by ourselves, estimate and see which method would be the ideal one for our particular case. In the literature, number of criteria by which methods can be compared, evaluated, and selected are proposed. These criteria under number 3 and 4 proposed in their own references are used only in their respective papers. I haven't found application elsewhere, so we have decided also in our previous research to focus on these 2 criteria by Benson and criteria by Park and Song. The first one is, of course, presentation of experimental actual data and the estimated ones, in this case, fatigue lives, in such scatter diagrams where we can basically see in a more illustrative manner. It's not very quantitative, so it's difficult to extract some actual information from it. We can only judge approximately whether these data fall within reasonable direction, so if they coincide better or worse. And additional information that is also present in this criteria is the percentage of data that falls within certain scatter bands. So this is very often used. We use it as well, but again, it's more qualitative, not so much quantitative method of evaluation. Again, if we are talking about more detail, we need some more substantial criteria, which then we can objectively compare. And for this, we rely on criteria for evaluation proposed in 1995 by Park and Song. They are much more quantitative. We have 4 parameters, in fact, 3 independent ones, and one, the last one, that is actually the average value of all other 3. But instead of explaining these formulas, I will just very briefly, for those of you who are not so familiar with these criteria, try to illustrate it very briefly. So those 2 goodness of fit, goodness of fit parameters are related to how well the experimental points and estimated values fall around this ideal line. So ideally, estimated values would coincide with the experimental ones, and all of them would fall on the same line, and this would be perfect, which is, of course, never the case, not even close. We usually have this kind of cloud of points, and we hope to keep them as narrow as possible and on this as close as possible to this ideal line. For this particular case, we here have this regression line, and we can see that it's skewed a little bit in different areas. How is that connected with those criteria parameters? If everything is ideal, individual parameters would have value of 1. Conventional error criterion is integrated in this evaluation method. And again, we can, of course, calculate percentage of data in different these bands, but of course, we use just the number of 3. Another advantage is that we have a lot of information and published results in literature, which also can be used as a reference. What we have done previously is we have established that looking at the data altogether contributes to a lot of averaging where some details are not visible. So we have proposed that such analysis is done in particular for these 4 subgroups. So material are grouped into low strength, high strength, and we consider separately low cycle and high cycle fatigue. And we can see here that these individual situations are not identical, so that in particular areas there are differences. This was applied in detailed analysis of steel materials, which was published recently, and we decided to apply this, in this case, to these 4 estimation methods for aluminum and titanium alloys. What we have done, we have collected data as we have done previously. So we have 30 data sets of aluminum alloys, 13 data sets for titanium alloys, and they are separated into low strength and high strength groups according to this criteria. And we have then proceeded with analysis. Here we can see how individual fatigue parameters, sigma f prime, b, so parameters for high cycle fatigue, correspond or are related to ultimate tensile strength. We can see quite a lot of scatter with certain parameters. The same thing is also here for epsilon f prime and c. So these are all the difficulties that various estimation methods are confronted, and it's difficult to achieve a large degree of accuracy. Here we can see what is more interesting and what we are actually interested in, the fatigue behavior, again, calculated for different total strain amplitudes, where we can see in some cases, some methods propose the unified expressions for both aluminum and titanium alloys. Here we can see that they are quite separate, but here we can see basically continuous distribution, as is the case also for these, as we go to the low cycle fatigue region is more pronounced. We have performed analysis for all 4 methods, but it's too much data, too many diagrams for this limited time. This is just illustration how these distributions look like. And what we can see here, that from this altogether diagram that shows all data together, a lot of information goes unnoticed. We can see here that some of these are much worse than the others, but in order to get better information, the same thing is also for titanium alloys. We actually need to look at these values of evaluation criteria that I mentioned before. And as this is initial part of the research on these estimation methods for titanium aluminum alloys, here we wanted to see how, what is the situation with this averaging problem, and we can see that it's quite pronounced. If we would look, as is usually the case, only on the results for all data together, we can see that these values are, some would say, not so bad, but if we look closer, we can see that particularly bad values of parameters and criteria are given in red. And here we can see quite a big differences in individual subgroups. The same is valid also for titanium alloys, with caveat that modified Park-Song method and FK method are not intended for titanium alloys, but we have included them in the analysis because also we have seen previously in some evaluations that some methods which are intended only for aluminum were applied also to titanium alloys. And so we decided just for the completeness sake to include it as well. Again, we can see that these methods again suffer to a certain extent from this problem of averaging, so that we can conclude after performing all these analyses and calculating these values of evaluation criteria that there is quite a large and inconsistent performance and accuracy across different material and fatigue lives subgroups. Luckily, if we use this detailed evaluation methodology, we can avoid it to some extent. We can see what is actually happening. And of course, this is valid only for these material data sets that we used here. Some sort of outlook, what we are going to do is with using more material data, we will then perform additional detailed analysis for all estimation methods which are proposed in the literature, also including these that require additional material parameters, and this will be a basis for development of new estimation methods based on the results that we achieve here. Well, thank you very much for your time, also to our supporters, and thank you.